Hey Trick Class, let's look at this set of notes 9.2, the law of sines. So what we're going to do here is begin to solve triangles that are no longer right triangles. So we have SAA, ASA, SSA triangles and their applications. So what do we mean by this? Well, first of all, we're solving now oblique triangles. So oblique triangle, you can think that just means it's not a right triangle anymore. So we have angles that could be all acute angles, something like that, or we can have an obtuse angle in there. So we no longer have a right angle involved when we're talking about oblique triangles. Now we're going to have these four cases to consider, right? ASA or SAA. So this would be, I'm given, so let me just show you the difference between these two. If I have two angles, so angle A here and angle B, they're known. I know their measures, and I know the angle between them, angle C, or sorry, side length C, not angle C, side length C, then that's a SA. The side is between the two angles. So this side I know is between these two angles. But if I knew angle A and angle B, but the side I knew was like side A, that's not between the two angles, then that is the SAA. So I know two angles, but the side is not between them. It's over here, in a different position. So that's the difference between ASA and SAA. All right, case 2, SSA. That means I know two side lengths. So let's say I know angle or side length C. I know side length A. All right, so I know two sides, but I don't know the angle between them. So if I knew the angle between them, that would be angle B here. All right, that would be SAS, which we have down there in case 3. But if the angle I knew was, let's say, C, for instance, over here, that's SSA. That's two side lengths are known, but the angle that is known is not between the two side lengths. I refer to case 2 as the pain in the SSA because case 2 is a problem case. We'll get to that shortly. But notice that is spelled out SSA on purpose. All right, we saw two sides and the angle between them when we were describing case 2. Case 4, obviously what that would be is I know all three side lengths. Okay. In all cases, case 1, 2, 3, 4, we want to know all three sides and all three angles. That's what it means to solve an oblique triangle. So no matter what information we have, the three pieces of information we have to find the other three. All right, so on this slide, everything that you know is in blue. Everything you don't know is in red. So you can see the two angles and the side between them. That's what we mean by ASA. Two angles in blue for this second case right here with the side not between them. Right? Two sides in blue, the angle given is not between them. Two sides in blue and the angle given is between them. And then all three sides. So those are the 5 cases that we'll have. All right, here's the law of sines. If we have a triangle with ABCs, any triangle, with opposite angles, capital A, capital B, C, okay? So A is opposite A, B is opposite B like we've been drawing. Then it will always be the case that the ratio, the sine of the angle to the side that's opposite of that angle, so sine of A to the angle that's opposite, that will be the same as the sine of B divided by the side length of its opposite, the sine of C divided by the side length of its opposite. That will always be the same ratio. Okay, that's what we mean by the law of sines. All right, now I also think of this the other way around too, meaning A divided by the sine of A is being the same as B over the sine of B. This is great when you need to solve for angles, and then this one down here is what you're solving. Set that one up if you're solving for side lengths. All right, and because of that, we have this, they're all three equal, sine of A over A, sine of B over B, sine of C over C. They're all three equal, so they're equal pairwise. So that means that sine of A over A is equal to sine of B over B. That's the first thing we saw here, all right? But it's also true that the sine of A over A is equal to the sine of C over C. And then the B is equal to C. So we have 3 different pairs of equations there. All right, all angles inside of a triangle, 45, 55, and then C, they have to add up to 180. So we can start there always. If we give them 2 angles, we can find the third angle. So 45 plus 55 plus whatever C is 180. Do a little math. That means C has to be 80 degrees. All right, now we want to set up the law of sines. So we can find side length C or side length B by using this pair that we're given, 45 degrees and 5 for the side length opposite that. So I can set that up. Sine of 45 over 5 is equal to the sine of 80 over C. Or again, I could do it with the 55 and the B. Sine of 55 divided by B. Those two ratios will be equal. All right, so there's what we set up. Again, I would personally, this is the PowerPoint setup, I would have set it up this way. That way, all I have to do is multiply both sides by this sine of 55, and I end up with B equals, I like to pull this out 5 times, and then you're just multiplying this over. So it's the sine of 55 up in the numerator, and the sine of 45 in the denominator. And that allows me a quick, easy way to solve for the unknown sides if they're up in the numerator like that. So personally, that's what I would do in both of these cases. I would have these set up with the reciprocals of these to have just that one step to isolate the unknown side length. All right, there's what we get. The sine of 55 over 45 times the 5 is about 5.79. When the number up top, the sine of the angle up top is the angle is bigger than the angle down below, it's going to stretch this number, make it a little bigger. So in this, because 55 is bigger than 45, we expect to be higher than 5. Now, if this had been a 35 and a 45, we would expect this number to be lower than 5. But because it was a bigger angle up top than it was on the bottom, we get a little bit bigger number than the 5 that's been multiplied by it. All right, doing the same thing with C, we would get 5 sine 80 over the sine of 45. So again, that's 80 is much bigger than the 55, so we're getting 6.96. It'll always be the case when you do these setups that the largest side length is going to be opposite the largest angle. All right, now this is what you're going to see a lot of times. Just solve the triangle and give you the 3 bits of information, and you have to find the other 3. So I encourage you to just draw a picture. It doesn't have to be to scale, like the angles don't have to be what you're claiming that they are. This is just to help you get things set up. So I draw my A, B, C. That's my angles. That's capital letters. Lowercase opposite, so this is A, so little a is going to be over here. All right, B, angle B there, so little b is over here. And so that means this is little c. So my big capital letters are angles, my lowercase letters are side lengths. So this is 20 degrees, this is 25 degrees, and that means I can get this one from the 180 rule. 180 minus 20 minus 25. So C is 135 degrees. There's what I mean by it's not to scale. So it's a very obtuse angle, and it looks acute. But it lets me know the third angle. Okay. Now it says C is 4. That means this side is 4. So now I know a side length and the angle opposite that side length. So I can set up the law of sines with the other sides. So I get A over the sine of 20 degrees is equal to C is 4 over the sine of 135 degrees. Again, there has to be a known side length and angle opposite pairing to be able to set up the law of sines. All right, multiplying away the sine of 20, I get A equals, I do 4. I do it like that personally. All right, and that's approximately 1.93. All right, and then B, same exact thing, except we would have sine 25 over sine 135. So again, you kind of see the benefit of setting it up in that format. It kind of gives us a formula to use in these cases. All right, this is about 2.39. So there is the law of sines with a ASA case. Again, I'm given this angle A, I'm given angle B, and I'm given C. It's the angle of the side length between the two angles. All right, now we're up to the pane in the SSA case. When we are given two sides and the angle that's not between them, so I'm given this blue side, I'm given this red side, but the angle I'm given is not between these two. It's not this angle. That allows this angle to be other things, and I can rotate around and get different possibilities. So if this, let's say this, hypothetically, this given angle, was 55 degrees, and this side length was 6 units, and this was 6.4 units. You can see I have a triangle there. But I could also have a triangle over here. So there's this possibility of another triangle. And then for other cases, like for other situations, like I'm given some angle, And let's say that this angle A, or this side length A, is only this long, and this side length is, this long. Now you can see I can't make a triangle. Right? And then for other cases still, and maybe this is 48 degrees, 4.5, let's make this 4. You can see that I can make one triangle here, but then over here I can't fold around and get another triangle. This side's too big, so it can only produce one triangle. So you have to understand, I'm given the blue length, I'm given the red length, I'm given this angle. I don't know how long this is, this side length. I don't know this angle. I don't know this angle. So when I'm just given two side lengths and the angle not between them, there's this ambiguity that comes into it. And it all depends on how these angles relate. Where this angle, or this side length going up by this angle, connects to this one. And this one is given a distance. So that means that where it connects to the other angle, that's its center on this kind of radius that spins around on this circle. And that will determine how many different triangles we can have. And again, depending on how long this angle that's opposite the angle that we're given is, we can go from, I have just one triangle that's possible, I could have no triangle that's possible, or I could have two triangles that are possible. One being an acute triangle and the other one being this obtuse triangle. So there's all these different possibilities that form when I have the SSA case. So that's, a lot of times we call this the ambiguous case, and the reason why we call that is because of the ambiguity. We don't know if we're going to get no triangles, one triangle, one right triangle in this case, or two possible triangles. So because we have SSA, one of these side lengths that will be given, no matter what, will be opposite the angle that we're given. And it's always going to be that pairing that shows up in this. All right. How does A compare to other side length I'm given times the sine of the angle that I'm given? So B sine A in this case is that vertical height. And when the side length that we have that's opposite the angle we're given is less than other side we're given times the sine of that angle, right, which is what we call H here, that means we're not going to be able to get a triangle. When they are equal, we get exactly one triangle, and it's a right triangle. Right? But if the side length that we're given, that's opposite the angle, is larger than B sine A, it's larger than that perpendicular height. Perpendicular height would be like right there. When this is larger than that, it kind of dips down and it swings back up and it hits again. That means that it's larger than B sine A, but it's not as big as, if you rotated this around, it's definitely not as big as side length B here. So when that's the case, we're going to get two triangles. All right, and then there again is B sine A. There's where that swivel begins, and you can see A is on this circle that's way bigger than the circle that radius of length B would be on. So A is greater than B in that case. All right, the side that's opposite the angle that we're given is greater than the other side length we're given. And when that's the case, then we'll end up with just a single triangle. All right, so in this case, again, the stuff that you're being given here is A's and B's and all that stuff. But just, I want you to see there that capital A and little a are opposite one another. All right, that's the one that we're multiplying by the other side length we're given. Okay, so in the scenario we have here, capital C and C are the ones that are opposite of each other. So in that case, we have, here's the capital C, here's the lowercase c, and then A is equal to 2 here. So we always start off with what the notation here called B sine A. B is the other side that's not the pairing, the capital letter and the lowercase letter, is the other side times the sine of the angle. So for ours, A is the one that's the one that's not in the pairing. So it's 2 times the sine of the angle that we're given, 2 sine 50. 2 sine of 50 is 1.532. All right, the side length that's opposite, C, is less than H. All right, this is H. So that means no triangle. I can't make a triangle in this situation. All right, so that's what you see here. There's the picture, kind of a little bit more to scale. I can't get, C is too short to get down there and touch the third side, so we can't form a triangle. All right, A is the pairing that the side length and the angle. B is the opposite, so this is kind of goes by the picture that we've been used to. And you can kind of dash this. This isn't actually a known side length. We don't know how long this side length is down here. That's our C. All right. This is A degrees, and then we have little a up here somewhere is 4, and B, this one here is, again, we always typically start off with that B sine A, but when the opposite side is bigger than or equal to B, we're just going to get one triangle. So A is greater than B, that implies one triangle. All right, so we can set it up. The sine of 60 degrees, right, is to 4, that's the opposite, as the sine of whatever B is to, what's opposite that, 3. So the sine of B is equal to 3/4, again multiplying this 3 over is all I'm doing, 3/4 the sine of 60. All right, so that means B, the inverse sine. So I get approximately 40.51. So that's about 40.5 degrees. So we can get C from 180 minus 60 minus 40.5, which is 79.5. All right, and now we're ready to solve for side length C. Now we can't use the Pythagorean theorem here. It's not 3, 4, 5 triangle, so don't fall into that trap. We have to use the law of sines here. So again, I am setting it up as I'm solving for a side length. So C, the thing I'm solving for, is to the sine of 79.5 degrees. As again, I always use the one that was given to me. So the side length there was 4 sine 60. All right, multiply that over, I get C equals 4. I pull it out, sine 79.5 over the sine of 60. So it's going to be a little bit bigger than 4 because that numerator is bigger, that degree of the numerator. So C is about 4.5. Right, always check. There's my largest angle, so that largest side should be opposite that angle. There's my next largest, that should be the one in the middle. There's my smallest, that should be the smallest side length. So you always check to make sure that your angles that are smallest or largest are opposite the sides that are respectively smallest or largest. All right, let's look at this one. We got A and A again. So we have our angle and its opposite side length being called little a and big A again. Okay, this is B, this is 9. All right, you can see A is not larger than B, so I could have no triangle, I could have one triangle, I could have two triangles. So I need to compute B sine A here. B is 9, sine of 40. It's about 5.79. So what we see here is A is larger than H. A is bigger than that, but A is smaller than B. Right, when that's the case, that means that we have two triangles. So what we have to understand here is when we set this up, the two triangles we're going to get are going to come from this angle B. When we set it up, the law of sine says, set these up, and I'm solving for an angle here. And on the unit circle, when I get an angle based on a sine, remember sine is the y-coordinate. This is cosine of an angle. This is sine of an angle. All right, that's the y-coordinate that we get that sine. But that y-coordinate could also happen over here. It's the same height, so it produces the same y-coordinate. And this angle right here would be like our angle B that we get that produces it. That's like the first B. But we could also get it from this obtuse angle that would produce that exact same height. And that would be like B2. That's the second possibility. So one is acute and one is obtuse. We have to keep that in mind when we have this situation. All right, so let's set it up. So I'm going to set up the sine of 40 degrees is to the angle opposite, or the side length opposite that, which is 7, as the sine of B, the thing that we're trying to find, is to 9. So do the math, I get 9/7. The sine of 40 is the sine of B. So B is the inverse sine of all this stuff. So B could have been 55, roughly 0.7 degrees. Okay, all right, that's B1. B2 could have been obtuse version that would give me this same one. Again, quadrant 2, that would be 180 minus this angle, which would be 124.27 degrees. Let's say 0.3 degrees to round to the same number of places. So those are the two cases we have to consider. We have to proceed through with B being 55.7 degrees and then start back over and proceed through with B being 124.3 degrees. All right, if this is the case, this is the 55.7 degree one, then that means angle C is 180 minus 40 minus 55.7. So C is about 84.3 degrees. All right, and then if we're looking at this other scenario, then this case would leave C as only being 57 degrees. Again, that's 180 minus 40, but instead of 55.7, now it's the 124.3. That would leave the 15.7 degrees for C. All right, now we set up our law signs to find side length C down here. All right, we know A, we know B, now we need to know side length C. So little c is to the sine of this, again, is the top one, 84.3 degrees, as little a, again, the one I'm given was, the pair that I was given was 7, and the sine of 40. So that means c, little c, is 7 times the sine of 84.3 divided by the sine of 40, which is about 10.8. All right, and the only thing that's going to change differently when we come down here is it's going to be that sine of 15.7 degrees over the sine of 40 in the denominator, which will make C only roughly 9 units long. So that's the different scenarios we have. Again, we got 1, 2, 3 pieces of information. There's 3 more that we have to find. So there was 1, it's the angle B, there's 2, angle C, and there was 3, side length C. All right, and then for the smaller one, angle B, that fourth piece of information could have been that angle, leaving C to be 15 degrees, and then setting up the law signs, little c is only 2.9 units long. So those are the 2 different cases that we have when we have, that's what it looks like. We have 2 different triangles. It all comes down to that second angle that you've set up and solved for. So there's the picture that we have done, showing you those 2 different possibilities that have a 9 and a 7 and a 40 degree angle opposite the side length 7. So we have 2 different possibilities, an acute triangle and an obtuse triangle. All right, it's not always going to be acute and obtuse. It could be 2 obtuse triangles, but there will always be one case where an angle is acute and one case where that obtuse version of that same angle. Because 180 minus acute angle is going to be an obtuse angle, but when we have the acute case, that other angle could be obtuse. It's not guaranteed that it'll be acute like it was this time. I mean, it was really close to being obtuse. It just depends on this other angle. All right, we got a surveyor measuring a mountain. He's taking a measurement here with this angle of elevation to the top. And then when he moves forward 900 meters, he has to look a little higher because he's gotten closer. So he has to look higher to see the top of the mountain. So he knows how far he's moved. He knows now the angle of elevation from his line of sight. Okay, so what we have to do here is a couple of different things. Number one, we have to figure out what this angle is in this second triangle when he's moved closer. So that's 47 degrees, and remember these are always complementary, so that means this is a 43 degree angle. And then this overall triangle right here has a 35 degree angle right here. So that means, again, this one that goes from the height of the mountain up is, again, 90 minus 35, which would be 55. So if that's the case, then this tiny little slither of an angle right here is the 55 minus the 43. So that's a little 12 degree angle right there. All right, I'm going to erase all this ink real quick. And so now I've got this angle that's 12 degrees, and that angle is opposite this side length, which is 900. So I can set up the law of sines, and what that'll give me is this side length here. And now I'm in with a 47 degree. I'll know this number right here, and I'm in this right triangle where I can just use right triangle trig to come up with that height. All right, so I'm looking for a side length, so I'll just call it C. Right, that's C right here. That's opposite a 35 degree angle. So that C is to the sine of 35, as 900 is that's the 12 degree angle that's opposite it is to the sine of 12. So again, I'm going to say C equals the 900 I'll pull out. The sine of 35 is being multiplied over, so it's up in the numerator. Sine of 12 down in the denominator. So this will be a little bit bigger than the 900. So I got 2482.9 roughly. All right, that would be meters. All right, and so now we're in this triangle. We know the hypotenuse is 24.9, and we want to find the side opposite. So that too would be the sine. So the sine of the 47 degrees. This is a right triangle, so I can just use a trig function. Opposite over hypotenuse. So h equals, so this is about 1815.86 meters. Okay, so that's this part. And then the height of the actual mountain, we'd have to add that 2 meters. So that would be 1817.86. Roughly 18. All right, so don't forget, little things like that to add those little numbers back.